Okay, in this video I'm going to follow up with the previous ones with my binary logistic regression example. We were looking at predicting the likelihood that individuals, students who seek services at a college counseling clinic would terminate within the first 2 months of onset of services. So for this variable terminate, that's our dependent variable. It's coded 0 for those individuals who did not terminate, 1 for those individuals who did. Our predictors were avoidance of disclosure, symptom severity, which were both treated as continuous variables. Sex is a dichotomous variable. It's dummy coded for 0 equals male and 1 equals female. I also had a year in school, whether they're freshmen, sophomore, junior, or seniors, but I'm not going to include this in the current illustration. So, if we go through the standard binary logistic regression option in SPSS, you can see that essentially we can model our data. We can even ask for predicted probability of the individual falling into the group 1. And then group membership, which is actually derived from those predicted probabilities to generate a predicted group membership. So, individuals that had a predicted probability falling into group 1 being less than 0.5 would be predicted to be in group 0. Those with a predicted probability equal to or greater than 0.5 would be predicted to be in group 1. So, just kind of showing this again, we have our predicted probability of falling into group 1. So you can see right here, these are all low probabilities, and consequently they were all predicted not to fall into group 1, but rather group 0. And then you've got some higher probabilities here, and these people were predicted to fall into group 1. So we can also run our binary logistic regression through using the Generalized linear models module in SPSS. So let's just do this. So we're going to go through. We can click on binary logistic. And the cool thing about the Generalized linear models option is that you've got a number of different possible GLMs that you can test out. So, but we're going to stick with binary logistic here. So our response variable was terminate. If we do have to specify a reference category. So we generally treat the category group 1 as being a target category, the group coded 0 as a reference category. So we're going to put our reference category being the lowest value. That's the first one. So so the group coded 0 will be considered the reference category. Under predictors, we can move our predictors over to the covariates box. Again, sex is a categorical variable, but it's already dummy coded, so we can go ahead and move this over to the covariates box. If we wanted to include year as a predictor, we'd have to move it over to the factors box, and then we would have to basically decide which group would be a baseline. So like in the previous video I showed using the freshman as a baseline. So to do that, to accomplish that, I would have clicked on descending. But I'm not going to include this just to kind of keep things a little bit simpler. So under model, we move our predictor variables over to the model box. These are the main effects. If we wanted to test an interaction among the predictors, we could just click on interaction, highlight the variables that are included in interaction, and it'll create an interaction term for us. Again, I want to keep this fairly simple, so I'm going to leave that out of our basic model. So under statistics, I'll click under include exponential parameter estimates, which will get me the odds ratios that we talked about in the previous videos. Under save, you have predicted value of mean or response, and that will literally get me the predicted group, the probability of falling into group 1. So this will give us the same thing that we generated through the other route. The predicted category will also be the same as the predicted group that we asked for through the other binary logistic regression route. And then the predicted value of the linear predictor, this is the logit score. So it's and so this is what allows us to model a linear relationship between our predictor variables and the criterion variable. We kind of go through an intermediary, which is the logit, and we can actually convert the logit back into predicted probabilities. The reason why this is important is because the relationship between your predictor variables and predicted probabilities is inherently nonlinear, and essentially, you could kind of think about it this way. If I had like a predictor variable, predictor variable x, and I had predicted probabilities of falling into group 1, ranging from 0 to 1, where this is probability at 0.5. Likelihood of falling into group 1. The relationship between scores on X and those predicted probabilities would probably take on more of an S shape. So essentially, as like in this particular illustration, as scores increase on X, the predicted probabilities are increasing, but the rate of change in those predicted probabilities is greatest, in this area right here, and essentially you're getting the probability falling into group 1 being more of a coin toss. Down in the tails, as you start to move out into the tails, the predicted probabilities are the amount of change in those predicted probabilities are decreasing, and essentially that's what happens. By the same token, if you had so this would be a situation where you had a positive relationship between the predictor and the predicted probabilities, but again, this is a negative. This is inherently nonlinear. So we essentially convert those predicted probabilities into logits and essentially form a straight line from that. So we can model the relationship between a predictor and the logit scores. And just pretend like that's a straight line. It's not very well drawn, but so essentially those logit scores can be converted back into predicted probabilities. So what we essentially do is we utilize a link function that links the predicted probabilities to scores on X, and that's where we invoke the concept of logits. By the same token, since I'm already here, we could also have a situation where our S-shaped curve looks like this. So there's a probability of being in group 1 and so forth. And so you can see in this case, this would be a negative relationship between scores on X and predicted probabilities. And by the same token, we could have a logit X relationship that would be negative. So that's essentially the way to sort of think about this. So ordinarily, nobody really cares to ask for this, at least as far as I can tell. I guess you could utilize this if you were testing your assumption that you have a linear relationship between your predictor and the logit scores. I guess you could actually, that might be relevant in that context, but you don't oftentimes see this when people are running logistic regression models. So at this point, let's run the analysis. I'm going to click on OK, and you'll notice that we have things that are fairly similar to what we saw previously when we ran the binary logistic regression through the other route. So you'll notice that this test right here, this is testing the degree to which your full model is an improvement over the null model. So if this is statistically significant, that means that you have a significant improvement in fit over the null model. So obviously in this case, you can see the p-value is less than 0.05. So we have a significant improvement in fit. These are, here we have walled chi-squared values, which actually in this context are going to match what you have right here for your walled chi-squared test, and the significance levels actually all turned out to be the same. the odds ratios that you have right here are exactly the same as what I showed you in a previous video, so there's not really much need to kind of further unpack that because we've already unpacked it. Some of the interesting stuff to note too is that you do get these various indices of model fit, and these are probably most useful if you're trying to compare different models in terms of fit. So you have like the deviance statistic, you've got the Akaike's information criteria and the Bayesian information criteria. So if I was comparing, say, two competing models in terms of their fit, essentially the model that has the lower AIC and BIC values, that would be the preferred model through that comparison. So now let's look at our data set, because we've now asked for the Logit scores, which is what we have right here. Here you can see we have our predicted values, which are literally the same as what we had gotten previously. So these are exactly the same. The predicted group values, these are exactly the same as what we had previously as well. So let's take just a few moments and look at the relationships between the logits, the odds, and probability. Logit essentially is computed as a linear function of the predictor variables. So you can see right here, for instance, that essentially in logistic regression, the maximum likelihood estimation approach is utilized to estimate the values of the intercepts as well as all the predictors in the model. And you can see that this linear model right here looks very similar to what you would have in a standard least squares regression. But again, the relationship, it is a linear relationship, but the linear relationship is between the predictor variables and logits, are basically what are referred to as log of the odds that the individual falls into group 1, and that's conditional on the set of predictors. So we can also through exponentiation, if we raise the base of the natural logarithms to the power of the expression on both sides of this equation right here, we essentially get the odds of the individual falling into group 1, which again is conditional on the predictors. So essentially, if we exponentiate the logit, we end up with the odds. And then if we want to compute the probability that the individual falls into group 1 using which is using the standard 0 to 1 scale that we're all familiar with, all we have to do is take a ratio of the odds. So we just take the odds divided by 1 plus the odds that the individual is falling into group 1. So let's go back to our original data set. We had our logit values right here, and logits basically range from negative infinity to positive infinity. Odds range from 0 to positive infinity, and as we know, probabilities range from 0 to 1. So the thing about it is that the reason why we care about this, again, is because the relationship between predicted probabilities and scores on the predictor variable is essentially nonlinear. So we utilize those logits as a way of establishing a linear relationship. So let's just take this particular logit score and work backwards for a second. So I'm just going to use Excel right here. I'm just going to put that value in here. And in terms of the odds, all I have to do is just exponentiate it. So I'm just going to take the base of natural logarithms and raise it to the power of the logit, and that gets me the odds of being in group 1 relative to group 0. And then, so essentially, all I've done in this case is just this little component right here. So I've just generated an odds. And then if I want to generate the probability, I'm just going to take odds divided by 1 plus the odds. So here I'm just going to say the odds divided by 1 plus the odds, and there's my probability. So and I can easily just kind of go back to the data set. I'll just go ahead and take a few more of these to illustrate my point. So we'll just make these all, take these logits as well, and compute the odds. And so there they are, and then their associated probabilities. So, as you can see, if I just take the actual probabilities that we computed based on the data, how many actually requested, you'll note that these are exactly the same. So that's the relationship between logits, odds, and probabilities. Now, if you want to go a little bit further and see how the probabilities are computed with a little bit more mathy explanation, we can even go further into it using this formula right here. And it looks pretty scary to some folks, but it's really not as bad as it looks. First of all, as you're looking at this, you'll note that this part right here is nothing more than the computation of the logit. Okay, so all this part right here in this equation is the computation of the logit. Then, if you take, so if you exponentiate the logit, which is what we just saw in the previous slide, then that gets you the odds. So now we have the odds. All right, and we saw that if we take a ratio, if we take the ratio of odds here, if we take essentially the odds of falling into group 1. Let me just write this out here. So if we say the odds of being in group 1 over 1 plus the odds of being in group 1, that yields a probability of being in group 1. And so as you can see right here, if this is odds, this is the numerator right here, and then essentially all of this is the denominator of our formula. So as you can see, we can actually compute the probabilities directly utilizing this particular formula with substitution. So like I said, it's a pretty mathy explanation, but it's I think interesting nonetheless. So if we want to compute the probabilities, then what I've done right here is I've just gone ahead and taken the coefficients out of our output file. So you can see that these were the coefficients. There's our intercept, regression coefficient for avoidance of disclosure, symptom severity, and sex. So essentially I can just model this using this particular equation right here, just through some substitution. So here's our equation. So this is just the essentially the odds. This is in the numerator of our formula that I just showed you. So this is the odds of being in group 1 relative to group 2, divided by 1 plus those odds. So that's it right there. And so there's my probability value. And so essentially all I'm doing in this case is I'm just taking, this is the intercept, and actually I need to make sure that I specify these properly. Need to lock my cells. Okay, so there's the probability, and so as you can see, it's just basically taking the intercept plus each of these regression coefficients times the value associated with each case, and that's what gets you the linear component, and then when you exponentiate that, that's what gets you odds. So there's the probability for person or case 1, and then these would be the probabilities all the way through person 9. So if you want to really just prove this, we can see right here, these are the predicted probabilities all the way through group 9. I'll just cut and put them side by side so you can see, and there they are. They're exactly the same. So the long and short of it is that those are the relationships among the logit, the odds, and predicted probabilities.